If your model's 90% confident isn't actually 90%, accuracy won't tell you. These true scores will. This is the setup you'll be able to run after this, which scores your probabilities with 2 measures and picks the right one for your goal. I'm Professor Pi, teaching AI foundations with simple Python. Too many workflows stop at accuracy or AUC and call it a day. That misses a big question. Are the probabilities themselves any good? In production, you often act on probability thresholds, or you price risk, or you rank candidates for human review. Success means trustworthy probabilities that match reality well enough for your downstream decision. Scikit-learn gives us tools to measure that. We will see 2 complementary scores and how they guide different choices. Start simple. One metric treats probabilities like predictions you can average and measures how far they are from the truth. The other treats probabilities as a likelihood and heavily penalizes confident mistakes. One rewards calibration, the other punishes overconfidence. Both matter, but for different tasks. We will build a tiny pipeline you can run quickly. It will score a fake model with both metrics, push an overconfident variant, train a classifier, measure top 5 ranking, and finally, calibrate a tree and compare choices. This keeps the ideas concrete and shows how metrics change which model you pick. Now let's score some probabilities. This snippet evaluates probabilistic predictions using scikit-learn's Brier Score loss and log loss. The list Y true holds binary outcomes, while ppred contains predicted probabilities for class 1. The function Brier Score loss computes the mean squared error between probabilities and outcomes, highlighting calibration quality. The function log loss computes the negative log likelihood, strongly penalizing overconfident wrong predictions and aligning with maximum likelihood training. Together, these metrics expose different failure modes, even when accuracy might look fine. The printed values show probability accuracy and penalty for overconfidence, clarifying whether your probabilities are safe to trust. Read the 2 numbers as different lenses, one for average probability distance and one for punishment of overconfident errors. Next, we will exaggerate confidence and see what breaks. This example exaggerates confidence to reveal calibration risk measured by scikit-learn's Brier Score loss. The variable p over pushes probabilities toward the extremes while clipping to valid bounds, simulating an overconfident model. The function Brier Score loss is applied to both the original ppred and the overconfident p over to compute a fair average squared error comparison. The variable gap captures how much the Brier Score worsens when you trust probabilities too much. Increasing the scaling makes probabilities even sharper, generally increasing the penalty. Decreasing it softens the change. A positive Brier gap means overconfidence hurt probability quality, which directly threatens thresholding and cost-based decisions that rely on probability as a calibrated signal. Next, we will train a small model and inspect how well it ranks the top candidates. This code uses scikit-learn to train a logistic regression and then ranks test items by predicted probability. The function makeClassification creates a small synthetic dataset, and a simple train-test split is formed by slicing. The estimator CLF is fitted on the training data. Then predict-proba returns class 1 probabilities for the test set. Sorting these probabilities in descending order selects the 5 most confident positives, and the mean of the corresponding labels yields precision at 5. Increasing n samples can stabilize this ranking estimate, while too little data can make it noisy. The printed p at 5 shows how well your model prioritizes likely positives for top K decisions. which matters when you only review a few candidates. Next, we will try to fix a biased model with calibration. This snippet uses scikit-learn's CalibratedClassifierCV to fix a decision tree classifier's probabilities with isotonic regression. The variable dt is a shallow tree trained on the same training data, which can produce biased probabilities despite decent accuracy. The object, CalibratedClassifierCV, wraps the tree and learns a non-parametric mapping from raw scores to calibrated probabilities using cross-validation. Brier scores are computed for the uncalibrated and calibrated predictors, and their difference, G, reflects the improvement from calibration. Increasing max depth often worsens calibration and can make isotonic gains larger. Reducing CV may speed fitting, but risk overfitting. A positive Brier gain indicates more trustworthy probabilities after calibration. Next, we will compare the calibrated tree and the logistic model using both metrics to choose which to deploy. This example compares two scikit-learn predictors, our logistic regression and the calibrated tree, using log loss and Brier score loss to guide decisions. The variable TP holds calibrated tree probabilities, and probs holds logistic probabilities. Log loss emphasizes ranking quality and punishes overconfident errors, so the lower log loss model is chosen for rank-sensitive tasks. Brier score reflects overall probability accuracy, so the lower Brier model is preferred for calibration-sensitive thresholds and cost-based decisions. If you increase the tree's depth, calibrated Brier may improve or degrade, depending on overfitting. The printed choice clearly ties the metric to the task, ensuring you deploy the right model for each goal. In a real project, this maps directly to choices you make at deployment. If you need to show the top 5 candidates to a human, pick the model with better precision at 5 and lower log loss. If you are thresholding for alerts or pricing risk, pick the model with the lower Brier score or calibrate an existing model first. Recap. What it is: Brier score measures average squared difference between predicted probability and outcome. When to use it: for calibration-sensitive tasks and thresholding. One caveat: it can hide severe overconfident mistakes that log loss would reveal. Wrap, punch. One practical next step is to tune the calibration procedure or the tree complexity. For example, increase or decrease tree depth, and remeasure both Brier and log loss to see where trade-offs lie. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.